While we were doing the liquid, so I tried doing the liquid hydrate and I know, okay, the hydrate. So that you have to allow as well. But before I look at it, do I have to use that as salt, or can I do it without it around? So instead of allowing LH2O to be salt, can I just put
Yeah, I mean, it's a little bit more complicated than that, in part because you generate illuminate, right? So formally when we think about the mechanism, we'll often think about just the hydride, and I show that in terms of nuclear filtration. But remember, what can help you draw the mechanism is once that aluminum adds in, you've now lost that aluminum hydrogen bond. And so if you want, what you could do is at that point, it's kind of like dieball-ish to an extent, where you now have, you could also have it coordinate with that illuminate as well. Doesn't really matter. At that point, I think we've got a lot of options, as long as we show the elimination, and you sort of have the general idea that it's addition of a hydride followed by elimination. All right, guys, we're going to go ahead and get started. I just want to make one announcement before I get going and forget to tell you guys this. Actually, two announcements. So the first one is, again, quizzes next week. I was realizing, as I've been going through the carboxylic acid chapters, there's really not too much chemistry that we're learning within carboxylic acids that's all that new. So hopefully that shouldn't be a problem for you guys to get all the chemistry down. I've written all the quizzes already, and what I'll tell you is the sort of structure that I just wrote sort of across the board. For everybody, I had one sort of, here's a reaction, what's the product, and what's the mechanism, similar to kind of how I had in the handouts. And there's one for everybody that's going to come from organic 1. There's one for everybody that's going to come from the carboxylic acid stuff from today and from yesterday. And then everybody will also have a short synthesis problem as well. And again, for a synthesis, you're going to need all of that. So hopefully that should be motivation to sort of focus on one of the things that I think is most important, which is sort of really understanding the mechanisms. Again, with that sort of idea that mechanisms, if you know the mechanisms, if you can understand the mechanisms, then everything becomes at least a little bit easier. Still obviously a challenging course, but at least it's hopefully not so unbearable. Second point that I wanted to make, and this is just a suggestion, obviously I'm not going to be able to change your guys' habits a bit, but I got a couple emails and was hearing rumblings that I had sort of told you guys that LAH didn't reduce carboxylic acids. And I think what that stems from, and I'll try to be a little bit more complete on the board, what I had said was that carboxylic acids do reduce them, but the deprotonation makes the reduction slower. Thus, if you read in the text, it says that you have to heat it a little bit. I think what that stems from, in part, is the fact that I sort of noticed that when I drew on the board, I didn't sort of complete it. I sort of said it, but didn't complete it. I went back and sort of watched the video just to make sure. But I think what you guys should all sort of think about, I think, you know, when we're here in class, I think oftentimes you guys get in the habit of just writing down notes as quick as possible and might not be necessarily paying attention to things that are said. And that's fine, you know, you sort of are focused on making sure that what's up there, and you're spending a lot of time focusing on what I'm writing down and making sure you get it in your notes so you can go back and look over. But remember, I videotape all these lectures. And I think that it would be worth your while to take advantage of the fact that I do that and spend a little bit more time perhaps paying attention in the lecture rather than trying to scribble down everything that I'm writing on the board. I think that oftentimes if you're trying to keep up with what I'm writing down, that you might not necessarily be paying as much attention. So that's just my suggestion. Again, I know a lot of people are learners, and you can write down stuff and you can learn based upon writing down things. But I just wanted to sort of make that one point, and I would just say that, you know, I found, and this isn't necessarily a good thing because my notes became horrendous, but when I started doing really well academically was actually when I stopped worrying about taking notes that much. I would really try to genuinely focus on what the professor was saying and really try to absorb what they were saying. And I think, again, with the fact that we do have the stuff online, you guys do have a little bit more wiggle room. You don't necessarily need to be focused on making sure you get everything down because you can go and find it. Yes? That should be fixed. It's fixed, yeah. So what had happened was when I did it a couple days ago, the video, I didn't uncheck the private. There's like a little lock thing, and it made it private. It's now not available to search through YouTube. You have to go through my website. So it's not listed. I don't want just anybody necessarily being able to go out and find my thing, but you can find it through my website. So if you go and you just link through there, it should be good for now. Let me know immediately by email though if you find that problem again, and I'll go in and change it as soon as I'm able to. And so again, that's just my suggestion. You know, I heard it by one person, then I started hearing lots of rumblings that LAH doesn't reduce the carbonyl, and I suspect that it's because what I had written down on the board might have suggested that. And I think it's understandable, but I think it's also a result of more focus on trying to write down in your notes and maybe not necessarily paying as much attention to what I'm saying. So I just want to remind you guys that this is available as a resource, and you may want to take advantage of that by either rewatching the video or by paying more attention in class and not necessarily focus too much on writing down what's in the board. So that's just my advice. Take it, leave it. I'm just going to put that out there. Okay, so we've been going through a lot of reactions to date. I'm just going to refresh on a couple of them. By putting something into sort of perspective. Maybe it's something that might make you remember this. I think it's kind of interesting, and this is sort of related to research in my lab in terms of decarboxylations. So if you remember, decarboxylations result in leaving carboxylic acid. So if you heat something really, really hot, you end up doing a decarboxylation. The mechanism at those high temperatures, you could draw a number of different mechanisms, either some small amount of deprotonation followed by decarboxylation. Sometimes these are run with a little bit of base to actually deprotonate it. Or you could even start thinking about at that point perhaps homolytic bond cleavage, where you're making radicals and then having radical-based things. Again, at those very high temperatures, you can imagine a lot of things taking place. Turns out that this is a molecule that we're interested in our lab a lot to get entry into these molecules that have some therapeutic potential. And this molecule in particular is one called meconic acid. Again, this isn't really, you're not going to be like quizzed on what is the name of the structure. This is just some example of where decarboxylation comes out and where you can sort of remember that it's thermal. So meconic acid is actually found to sort of a major natural product in like poppy seeds. So a lot of times opioids will actually have as much as 5% of this in there, and so sometimes it's used as a detector and sort of a tracer to see if if there's been opioids around. It's not active. It's just sort of there. But what's kind of interesting is that a product that we work with a lot in our lab is actually a decarboxylated version of this. And so you take this molecule and you heat it to like 250 or 225, I think. And what you get to is this molecule here where you've effectively done a decarboxylation. And we actually use this reagent, use it a little bit in some of our studies. And I think what's kind of interesting about it is that the name of this compound is actually pyromeconic acid. And I think one of the things that's interesting about this is here's a compound that's used. You can actually buy this, and it's got a name, in fact, built within it, right? That basically is telling you that you take meconic acid, you heat it, right? So pyro, right, is sort of like, and you guys are big like X-Men fans or whatever. Isn't that one of the guys' names? That does the fire, right? So, or pyromaniac, right? So this sort of idea of really super hot temperatures are sort of used to convert this molecule into this molecule. And it so happens that this is called meconic acid, and so the name they gave this, because of the chemistry involved, is pyromeconic acid. And so people use this for various things. Again, we use it in our group for chemistry. On occasion, it doesn't actually work that well. There's other versions of it that we generally use, but I thought that was interesting in terms of the name. So anyway, a little side note. Yeah. So that's what I'm saying. So for decarboxylation, why don't I draw a couple things that you could in principle do, at least in terms of thinking about it. We did see decarboxylation. So one way that sometimes, if you're taking, say, something like benzoic acid, well, I don't know why you would ever take benzoic acid and try to make benzene from it, but if, say, for example, you were, you can, in principle, get this to go just thermally. And again, the book really doesn't discuss the mechanism, but at least for your guys thinking about it, what's specifically happening there, I'm not entirely sure, but at least in terms of thinking about it, you can probably imagine a couple things. First of all, you know, a lot of these things we discuss equilibriums, right? And something might get deprotonated by something else. Maybe there's something in solution that's able to deprotonate this. Or sometimes, in fact, people will use to accelerate these processes base or certain metals like cuprates, sometimes like silver salts and so forth, can help accelerate this. And those become a little bit more complicated mechanistically, but formally you can think about it as maybe a little tiny arrow that way, because obviously in certain solutions, this might not necessarily be how it is, but at least in terms of you conceptualizing it, you can think about a small percentage of it getting deprotonated, and then this setting off an anionic decarboxylation to generate the anion, which is then subsequently going to be protonated by probably whatever it was that put that off in the first place. The other way that you could at least conceptualize it is if you sort of remember, a lot of times at these really high temperatures, you allow things like homolytic cleavage. So the difference, if you can remember, homolytic cleavage versus heterolytic cleavage, most of the mechanisms that we deal with involve heterolytic cleavage, so the moving of 2 electrons at a time. Homolytic bond cleavage is the moving sort of 2 electrons at a time, or sorry, 2 electrons separately, right? And so if you think about, at least as an alternative, you can think about it, for example, dissociation, where through homolytic cleavage you might make a radical right, where you sort of do that homolytic bond cleavage, and then what can happen, right, is now you can do decarboxylation via sort of do decarboxylation via a similar type of fragmentation, which would then generate the benzene radical, right, which would then make the benzene. So either one of these ways, in terms of, when we're at these ridiculously hot temperatures, a lot of other things can start happening that we don't think classically in terms of a lot of the other chemistry. And so it is different in that extent, in terms of being a little bit out of the box. A lot of things that we start to see are perhaps analogous to, for example, you know, in mass spec, right? We saw a lot of fragmentation and stuff taking place in mass spec because we were at such high energy levels that things that we don't often associate as being normal might start taking place. So I think either of those mechanisms, at least to sort of rationalize in your brain how it happens and sort of keep track of atoms, is probably worth it. Okay? All right, so for today, what we're going to sort of continue on about is sort of carboxylic acid derivatives and sort of molecules that we would otherwise refer to or the way that I like to sort of think about it is molecules in the same sort of oxidation state as carboxylic acid. Right? And so really what we're kind of going to be focusing on is molecules. Again, when we look at something like a carboxylic acid, not sure oxidation state is necessarily the best way to think about it, but we can, in a way, think about this way to an extent in that, we think about different oxidation states and how carboxylic acids can often be, and this doesn't mean to be a retrosynthesis arrow, this is just some arrow. When we think about sort of the different levels of oxidation, at least conceptually, right, you have your sort of alcohols. Alcohols can be oxidized up to ketones or aldehydes. Ketones or aldehydes can then be subsequently oxidized up to carboxylic acids. And so at least when I think about sort of derivatives of carboxylic acids and a lot of things that we're going to sort of talk about today, you can oftentimes think about them being in this sort of carboxylic oxidation state, even though I'm not sure if that's the right technical name to it. And one of these that we're going to discuss today is, in fact, nitrile groups. Okay, so a nitrile group, I'll sort of try to draw a parallel there. The nitrile group, we've seen nitrile groups a bit in the past, but it's effectively a carbon bonded to another carbon, and that subsequent carbon being bound to effectively 3 heteroatoms in a way. Obviously, it's all the same heteroatom, but 3 bonds all going to a heteroatom, right? In this case, it's nitrogen. Same way as carboxylic acid all being bonded to that nitrogen. And certainly cyanides, or cyano groups, nitriles, we've seen them in the past as being products, fairly common products in a lot of your sort of textbook substitution chemistry, right? And the reason for that is that the ability to make nitriles is fairly easy using sources of cyanide, right? So lithium cyanide, sodium cyanide. And do you guys remember what the reason is that this is a really good nucleophile that can do a lot of this chemistry? So why are sodium cyanide, lithium cyanide, why are these good nucleophiles? Do you guys remember? Say it again? So you've got a carbon ion. Okay, this is actually fairly stable. Like cyanide's actually a decent acid. So it's not that it's a strong, but yes, it is charged. So that's good that it does have that charge that it would like to get rid of. So that certainly makes it better. But say compared to something like butyllithium. Here, yes, so it's sp hybridized, which is kind of a little bit what gives it its acidity and makes the anion a little bit more stable. But there's also something about the geometry of that sp hybridization that makes it nucleophilic. Exactly. So it's very slender, I guess you would say, right? It's if you're having cyanide attack something, it's like poking it with a pencil, right? It's narrow. There's not a lot of sterics involved in it because it's linear. And so from a steric standpoint, cyanides are good nucleophiles, again, because they don't really have a lot of bulk that's going to be coming with them as they're attacking the electrophile. Again, we've seen this with alkynes as well, right? So alkynes are good nucleophiles in part because, and we like to use them a lot, in part because the sp hybridized nature allows us to deprotonate them fairly readily compared to other nitrogen sources. But at the same extent, they're good at doing substitution chemistry because of the fact that they have this sort of narrow shape to them. So making cyanides is a very, it's going to be a fairly useful way for us to make carbon-carbon bonds. And then furthermore, cyanides are simply a hydrolysis away from carboxylic acid. Okay, and so if you're able to, this is an example where you could, if you have an alkyl halide and you want to sort of attach CO2 to it, you've got a couple options, right? So let's discuss that really quickly from a synthetic standpoint. So if you have, say, an alkyl halide, right, and what we wanted to do is convert this into a carboxylic acid, we have a couple options. One that we saw last week, towards the end of last week, was how? In a two-step process. Yeah. Right, but alkyl bromide is not going to react with carbon dioxide. You have to convert it to the Grignard first, right? And so one way that you could do this is first treat it to magnesium, right? That's going to make the Grignard. And then you're going to take that Grignard and you're going to subsequently treat it with carbon dioxide. And then following a workup, or I'll just say CO2, because again, we discussed it could be a solid or gas. But here's an alternative way to go about it, right? You could, for that same alkyl bromide, another option would be to take it and treat it with cyanide, so cyanide, lithium cyanide, sodium cyanide, and then subsequently hydrolyze that down. Okay? From a mechanistic standpoint, again, the hydrolysis of a cyanide is going to be, again, very analogous to all this chemistry that we've seen, whether it's transesterification, whether it's acetal formation. These reactions are all virtually identical, right? And so if you were to start thinking about the mechanism of this transformation, and let's go through it together, what would be the first step? What's the strongest thing in this reaction? Sulfuric acid, right? And so we've got sulfuric acid in here. So we take cyanide, it's got a lone pair there, right? That's going to be able to react with the sulfuric acid, which I'll just abbreviate as H+, right? That's going to activate that nitrogen, right, in the same way that we would say, for example, with carbonyl, okay? And now in a solution of water, right, what's going to happen? Water's going to attack where? Carbon, again, reminder to everybody, this is one of those hopefully organic 1 mistakes that you guys have all gotten through organic 1, so you're not going to make these mistakes again. But you're not going to have the water attack the nitrogen and generate a Texas carbon, right? You need to attack the carbon right adjacent to here, right? Yes? Somebody say something? Oh. Okay. This stage, again, we're going to get a proton transfer from the hydrogen, sorry, from the oxygen. We're going to take one of those protons, it's going to go over the nitrogen, so I'll just draw that out. Okay, this is going to lead to, at this stage, there's a couple different ways that we can go about this mechanism. Okay, but again, we have this aminium, right? This is actually going to be a fairly quick process, in part because this is going to be more stable than this. Why is this more stable than this? Resonance, right? That's generally what I'm asking. The answer is resonance. Okay? And again, water's going to add in. Again, for the sake of time, right, what I will do is, I will just say, again, once we add in, and for the sake of time, what we're going to see here, right, is that you're going to get the proton transfer, we're going to lose ammonia, right, or whatever, I'll just draw it. And then following deprotonation, what will be left with is our carboxylic acid. Right, so again, this mechanism, while it's new, you guys might never have seen this before unless you've read ahead in the textbook, this mechanism is the exact same thing as the transesterification, the exact same thing as hydrolysis of an ester. well, it's not exact, because then it would be exact, but it's in terms of the overall process, you're protonating a heteroatom, right, on a sp, in this case sp hybridized, in the other case is the sp2 hybridized carbonyl, and that's simply going to set off a series of additions, proton transfers, elimination processes, or sorry, leaving group processes, and it's eventually going to get to the carboxylic acid. So you should be able to see parallels between the hydrolysis of a nitrile and the hydrolysis or modification, for, if you want to call it that, of a carboxylic acid. Do you guys know? So when I discussed transesterification, I sort of mentioned that it could go in reverse and it could do hydrolysis, right? I sort of showed that and said you guys should walk through it. Does anybody know why it's called sometimes saponification? Yeah, so let me just, so soap, many of you guys know, right? Soap is sort of, oftentimes what you have is some big greasy side chain, right? Followed by a carboxylate, right? And so this is just sort of a little tangent that I think is kind of interesting, right? And so generally what happens in soap, right, and one of the things that makes soap special, right, is that you have you have a whole bunch of these line up, right, because the greasy sides all line up. Sort of your hydrophobic side ends up on one side, your hydrophilic ends up on the other side. That's why sometimes when you get bubbles, for example, in water or whatever, you've got sort of water on one side and you've got sort of air on the other, and you sort of get these spheres. So this is soap, right? And again, one of the fancy things about soap is that you can use water and it will get rid of things like grease and other more organic soluble compounds. The way that you make soap oftentimes is by hydrolysis of certain lipids, fats, so forth. And so these can come from various sources. But formally what you're doing is you're taking some type of, I'll just say R, because there can be various degrees of this, but you're effectively taking some type of an ester and you're hydrolyzing. That's how you get this sort of soap. So I thought that was kind of interesting. Anyway, so this is saponification, and literally can make soap. All right. Okay, so nitriles can be versatile, obviously. It gives you a source of nucleophilic addition if you want to sort of add a carbon across there. Nitriles can also be used, so we've seen them react with alkyl halides. You can also have nitriles react, you can also have cyanide react, and we did see this a little bit last semester perhaps with just cyanide gas, for example, or you can also use things like lithium cyanide in following workup. Aqueous workup, what you're going to end up with. Right? And if instead you do an acidic workup or you have acid and water, what that's going to allow you to get access to now is things such as proton source. Again, that could be useful to, for example, get to alpha sort of hydroxy carboxylic acids. So that's just another example where we've seen the versatility of cyano groups. Okay, I'm going to take a slight detour now. I'm going to talk about a few other functional groups or derivatives of carbonyls. And what we're going to discuss a little bit is the sort of relative reactivity of them. So I'm going to put up a few examples of carbonyls that we'll see that will be important. We've seen in some of these instances how you actually can make them. and we'll sort of refresh on that. But I'd like to just sort of put some up here, and what we can discuss is the sort of relative reactivity of each of these and how they might be valuable. It will also be worth it to sort of have the names. So in this instance, we're going to be discussing some fairly important structures, and so this is an aspect of where it's going to be worth your while to sort of know these names. I may say them on occasion without even necessarily telling you what they are, but I would say that it's worth it to know these names, and we'll discuss them a little bit more. So again, if you have a carboxylic acid derivative, but instead of an OH, you have some O alkyl group, like a methyl group or an ethyl group. What's this overall group called? An ester, right? That should be one that perhaps you guys have sort of picked up. Every once in a while, you guys will hear a term. Some of you may have heard it, some of you might already know this, but you'll hear something called a lactone. Does anybody know what a lactone is? Yeah, so lactone is an ester, but in a ring. Okay, so if you have a sort of an ester in a ring, it's called a lactone. Now I'm going to make one sort of little point here about the differences in reactivities of two molecules that would otherwise look identical. If I were to come up here and say, hey, which one of these is more reactive, maybe somebody would have an idea, but I think it's worth mentioning right now. Can anybody predict? One of these is quite more reactive than the other. Yeah. Okay, so I've heard of steric argument. Okay, so if you were to hydrolyze both of these, saponify both of these, basically make the carboxylic acid from these with acid and water, I've got a vote for the ester. Is that what you said? In part because the thought is that maybe a lot of this other stuff here might lead to sterics. That's a decent thought. So I'll just tell you, let's just say a 6-membered ring, just so that there's no ring strain. But yeah, certainly if it's like a 4-membered ring, yeah, that's gonna drive it just based upon the wanting to open up the ring strain. But considering all things equal, say a 6-membered ring where all things are equal. So we've got a steric argument, yeah. Yeah, this is kind of this is probably a tough question for you guys, for me to ask you guys. Yeah. Say that again? I think that's what was said before, the ring strain. Yeah, no. Let me follow this up with a second question and start to get you guys in the direction. Why is an ester we've already seen this, right? So hopefully you guys all know. What's more reactive, a ketone or an ester? So ketone. Why? Stabilized by what? So in a way, I think you're getting right there, right? So here, sort of resonance, right? Right. So it's sort of stabilized. I think it's kind of what you were getting at, right? You have this resonance stabilization, which effectively helps stabilize the overall system. And that may be a little counterintuitive, right? Because to the same extent, oxygen is more electron withdrawing than a carbon, right? And so you might assume that maybe that oxygen's pulling electrons a little bit more. If I were to draw this out, right, what we would see, right, is, again, for a sort of a pi system, so one of the things that hopefully you guys have thought about a little bit, but we'll sort of rediscuss it right now. It's very valuable when you guys are thinking about chemistry, specifically nucleophile, electrophile chemistry, that we think about antibonding orbitals, okay? And so when we're talking about antibonding orbitals, just as a quick refresher, right, we were really introduced to antibonding orbitals when we discussed SN2 chemistry, right? And within SN2 chemistry, you have your leaving group, right? And you get this attack. And where the attack takes place, right, is via this antibonding orbital. So when you have a bond, say this one right here, there's sort of this enthalpic energy that's gained when you make the bond, right? And so if you have an electron coming in from bromine, and you have an electron coming in from this carbon, what that leads to is the sort of bond. We'll refer to that as the sigma bond. It's the bonding orbital, right? But the net sort of result is that you still have an orbital, right, that's sort of left over. And this is oftentimes what we call the sigma star. And again, there's some quantum chemistry behind this. But the general idea here is that that antibonding orbital, at least for a sigma bond, is directly on the other side, effectively opposite the sigma bond. So, so you have this sort of sigma star here. In pi systems, again, this just has to do with, I don't understand all the math necessarily behind all the shapes of this and stuff like that. But what I can tell you is that when you have a situation where you have a pi system, there is also a pi star. Okay? And this pi star isn't necessarily directly behind it. It's this thing called the Berge-Dunitz angle. It's a little bit more advanced. But it ends up being effectively it's effectively somewhere in between. I think it's like 109 or something like that in terms of off orbital. I forget exactly what that number is. But it's at an angle such that when you attack something like a carbonyl, where you're attacking it from is at the pi star, right? If you're breaking a pi bond, you're attacking in the same way as if you're attacking the carbon and you're having a sigma bond leave, you're attacking the sigma star. If you're attacking a pi orbital, or you're attacking a pi bond, and you're breaking that pi bond, where you're attacking it from is the pi star. So that's where the sort of anti-bonding orbital of the pi system is. Okay? And in a standard system, right, that's going to be where, even in a resonance form, that's going to be where the electrons sort of donate into that resonance form. So if you've got a set of electrons, they're going to sort of donate into that sort of pi anti-bonding orbital. Okay? Now, in a system where you have something like a ring, even if it's, say, again, perhaps we'll do it in a cyclohexane because we're used to at least seeing chair conformations being a three-dimensional representation of, you know, at least we're a little bit comfortable seeing chairs in 3 dimensions. Where are the lone pairs on that sort of oxygen? You've got 2 of them, right? You've got one that's on the outside, and you've got the other one that's sort of axial. So you got, just like in a chair, you've got equatorial, you've got axial, you've got effectively vertically down here, right? And then you've got sort of equatorial here. And it turns out that in general, the thing with the lactone is, right, whereas in an ester you've got free rotation around here, which will ultimately allow you to have fantastic overlap. In the case of something like an ester, you don't necessarily, or lactone, excuse me, you don't necessarily have quite the same overlap. And so, as you can imagine, if you have, say, the Berge-Dunitz angle there, I'm really not doing a great job justifying my point here, but you can imagine that based upon the sort of constraint of the ring, it may be a little bit more difficult to get that alignment. And so generally lactones are more reactive, in part because the ability to subsequently stabilize and have that resonance stabilization is a little bit more deterred. So they're fairly similar, but there is this little difference. Again, maybe I might have confused you guys more than anything there. But perhaps it's a little bit more grad level stuff, but that's the general sort of idea, is that lactones, you don't necessarily have that same degree of resonance stabilization. And that might just help you sort of remember these. So again, lactones are a bit more reactive, usually. Okay. All right. So what else do we have? Again, one other one that we should know quite well at this point. It's one of the most important biological carbonyls that we have. is this molecule here. What is this called? An amide. Sometimes in the same way that you refer to amines as primary, secondary, tertiary, sometimes we can also refer to sort of amides as sort of primary amides and secondary amides based upon the substitution there. But we'll just call it an amide. The other one that we see, and so in the case of an amide or an amide, we also have a cyclic version of this as well. Okay? And in this case, this is probably something that you guys haven't. Anybody know what this is? Okay? So this is a lactam, so it's kind of like you take lactone and you add the am from the amine. Does anybody know a famous class of lactams? Anybody super interested? I'm sure none of you guys have any interest in medicine at all. Yeah. Beta-lactams. So who here has heard of beta-lactam antibiotics? Penicillin, right? So beta-lactam antibiotics generally have, and you guys were talking about strain a little bit before, beta-lactam antibiotics generally have this lactam within them. And so this is, there's usually, I think, some type of group over here. It's either 5 or 6 membered ring. But yeah, so there's, I'll just put, there's various changes over to this side, and that will oftentimes represent the different classes of penicillin drugs that we have. So beta-lactams are, your sort of standard penicillin class of drugs. So all those different penicillin B, penicillin, whatever, they all sort of have this 4-membered lactam in them. Okay. Now, in addition to these sort of 2 standard ones, again, where we have carbonyl on one side, you can also have, I'll just put this one over here, 2 other fairly common ones that we'll see are molecules like this, right? What is this called? An anhydride. Okay? This one in particular that I've drawn is called acetic anhydride. Okay? And in terms of perhaps remembering the name and putting some chemistry to the name, does anybody know why they're called anhydrides? What's that? Yeah. So again, where this sort of name started from, you have something, say for example, acetic anhydride, right? And so what acetic anhydride comes from is you take acetic acid, probably 200 years ago, somebody took acetic acid, they heated it, they found that what they were generating was some new compound that effectively had a molecular formula that was the same as 2 of them together, but had lost the water. Perhaps they ran the reaction and found that water was being generated. And so again, yeah, it's sort of like anhydrous acetic acid, right? Anhydrous effectively means sort of no water, right? So that's kind of where the name comes from. And then the one other one that we have that I have no idea why it's called this are things called imides or imids. I'll go through a fairly common one called, we've seen this a little bit, right? Where have we seen imides, succinimides, right? So where we've seen imides, in a way, is, right, like NBS, right? So NBS is basically N-bromosuccinimide. Might be a double bond in there, I forget, but it's this imide, and then you have the nitrogen bromine bond. So we've seen imides in the past as well, in terms of NBS. Okay? And so again, these are the sort of 6, probably the most important ones that we'll see. Once I erase all this here, we'll get into some interesting chemistry with imides that I think is kind of important in terms of how you might be able to use them in synthesis and some of the sort of important things with them. So again, so what do you guys think about the relative reactivity of these guys versus the corresponding amides? So how would you think that an anhydride would react in terms of at the carbonyl relative to, say, an ester? It's going to be more reactive, right? Why? Right, yeah, right. So that electron can effectively, you can imagine a resonance form, right, where those electrons are sort of back bonding into the other carboxylic acid, this ester here, which effectively effectively takes them away from this. And so again, instead of those electrons being delocalized into one of those orbitals, it's effectively going to be sort of shared between the two. And so there's less of an ability to have that sort of back bonding ability. In addition, the carboxylate is certainly a better leaving group in terms of a thermodynamic argument than something like ethanol. And so succinimides can also be hydrolyzed, and we'll actually give an example of that. A little bit easier, but still not great, but certainly perhaps easier than your standard amide. Okay, so that's just sort of nomenclature. That's the bigger reason I was putting out there. But certainly, if you use your intuition, you can begin to sort of think about how these molecules react and so forth. Okay, so within imides, I just want to sort of bring up one reaction of imides that could be valuable for you guys in, say, a synthesis problem. And I'm sort of shocked that this reaction isn't in your book because it's a classical way to make amines. So I'm going to teach it to you guys, and it's fairly simple. So if you have a standard amine, right? Yes. Why a nitrile is more. So an anhydride, right, than an ester? So I was just asked to clarify this being more reactive than this. Again, we're specifically talking about nucleophilic addition into the carbonyl in both cases. So let's just say hydrolysis, right? Which one's going to hydrolyze faster? So if we just imagine relative rates of acid and water, or even just water, you can sort of think about it from both, or actually let's do nucleophilic. Sort of make my point a little bit easier off the bat, and then I'll give you so this will be the thermodynamic argument, and then I'll give you the sort of more kinetic argument. If you add the hydroxide into here, right, what you're going to get to is your leaving group can be acetic acid, right? Whereas if you do the same thing here, you go through the mechanism, you can get an ethoxide as your leaving group. So from a thermodynamic standpoint, if you're treating it with, say, a Lewis, some type of nucleophile, an acetate is going to be a much better leaving group than an ethoxide. So that's one way that you can think about it, and that would be the sort of a thermodynamic argument under standard nucleophilic conditions. The other reason has to do with just sort of focusing on the sort of, maybe you can think about it as the stability of this. And so we sort of discussed previously, right, that there's still a certain element of resin stabilization two esters. What that effectively does, in addition to stabilizing the overall complex, also puts a significant larger amount of electron and electron density into this carbon region here. Okay? So, say for example, best way to sort of explain it. So again, the overall complex is stabilized by resonance forms, thus you're not going to as easily attack there. You could at least mentally perhaps think about it as being the carbocation character, right? And the amount of sigma star that's being generated perhaps during sort of this form, perhaps. Again, this I don't think is the best explanation because you could get confused by thinking that this would be a more stable one, thus a more likely to exist one. But you might think that this is fairly lower in energy intermediate because of stabilization with electrons there through resonance, or some fact. I tend to just think about it as the relative electron density throughout there. In that case, in this case, what you have is really two of those. Right? If you think specifically about this one here, certainly you can back bond the other way, but a certain amount of your ability to do that back bonding is prevented by these lone pairs being instead tied up in the other carbonyl as well. So in the case of acetic acid, right, it's not really going to matter that much because it would react with one rather than the other. But again, in that case, each of them only has, one of those is going to be more exposed than the other, or you're preventing roughly half, in other words, of that ability to back bond. So you don't get full back bonding, in other words, because it's having to sort of share that ability to back bond with a second carbonyl. Does that make sense? So, okay, I'm going to try one more time, and then I'll move on. Does it make sense that by back bonding you're stabilizing the overall system, thus stabilizing that carbonyl? Kind of, right? Now, if I told you that it couldn't back bond because it was being tied up in something else, you would assume that it would be more likely to react. That's what's happening. Okay, let me ask you a different question. Does the thermodynamic argument make sense to you? Great. So just, it's more important that you're able to remember things by having some type of rationalization to them. And so if the thermodynamic argument makes sense, then that's how you should be able to remember the relative stability of them. Okay. All right. Okay, so back to imids. Hold on. Okay, great. Okay, so I'm going to teach you guys one reaction with imids. This isn't in your book, but I think it's an important one. And it's something called Gabriel synthesis of amines. Okay, and it was in my textbook as an undergrad. And I think it's a good one. If you're going to introduce imids, I really think if you're going to start discussing imids and discussing some of the properties of imids, it doesn't really make sense to discuss them without at least bringing up Gabriel synthesis of amines, which really, I think, encompasses two of the really important factors of imids. And so if you had a standard imid, and we were going to focus on the acidity of this nitrogen-hydrogen bond, how would you think that would compare relative to your standard, say, for example, amine? Right? So if you have an amine, the amine's got a pKa of something like 30. If you have an amide, I'm not even quite sure what the pKa of that is. I should probably look it up, but you would assume that it's going to be a little bit lower. But when you get to this sort of ability to resonance stabilize in both of these, you actually have a fairly basic proton. And so it turns out that you can actually deprotonate imids fairly reasonably well. I wish that I'd written this down. I kind of decided this last second, but you can take this and I'll just say a generic base. I think it has to be a fairly strong base. Again, I forgot to write this down, but I think it's something like an alkoxide or something like that. I think is enough to deprotonate this. And what you're left with, right, is the sort of deprotonated version of it. And again, as you would imagine, this is going to be a little bit more acidic, in part because you can effectively resonance stabilize that negative charge throughout either one of these carbonyls. So you get that ability to sort of stabilize the system a little bit better. It also turns out that these can actually be fairly good nucleophiles, specifically when they're pulled back. And so one of the common ways that was historically used to make amines, right? So if you take, say for example, an alkyl halide. Let's say you take this molecule here, and let's say you try to treat it with sort of like lithium amide. What do you guys think is going to happen here? You're going to do an elimination, right? If you were trying to take that amide and you were trying to actually switch out the bromide with this, if what you were trying to do is make this compound here, it wouldn't happen, right? Because it's too strong of a base. What you would end up with is styrene. You would do just base-mediated elimination. Okay, so this is certainly a problem if you obviously amines are very valuable compounds. They're found in pretty much, I think, like I read somewhere, like 80% of drugs, for example, or 90% of drugs have a sort of a nitrogen somewhere in them, and so amines are important. And so if you're a synthetic chemist and you want to be able to make compounds that have amines in them, this is going to be a problem, right? And so it turns out, though, that one of the ways that you can do this is by taking advantage of two things about imids. And the first has to do with the acidity, right? So if you treat this, again, I apologize, I don't remember what the base is. Let's just say, I'll just say, because I don't know, I'll just say base. And then we subsequently take that protonated form of the imide, and now we say treat it to an alkyl bromide of some type. You'll actually displace the alkyl group, and you won't get the same problem with eliminations because the imide here is not nearly as good of a base. It'll simply serve as a nucleophile, and this is in some ways parallel to, I always hated that part in elimination, I'm sure you guys did too, where it's like, is this going to do elimination or is it going to do substitution, right? And the way that I usually like to sort of think about it is we'll make an argument one way or another, but certainly there are these competing factors. In the case of, say, an acetate versus sodium hydroxide, right, we've sort of seen that sometimes acetates can be better nucleophiles and they won't have as much of these elimination processes. So the same sort of thing is going on here. That's the first benefit to this process, so you can effectively make the nitrogen carbon bond that you're trying to make. And then again, because this hydrolyzes a little bit easier than, say, an amide, right? You wouldn't necessarily do this with an amide, but you can do this with these imides. You can take this molecule and treat it to, well, it's actually a decent nucleophile. We've seen this in the past with Wolff-Kishner reduction, but you treat it with hydrazine. And what the hydrazine is going to do is it's going to actually hydrolyze this overall system. And what you end up with is this plus your amine, which is what you care about, right? And so this is an option with imids that you can do if you want to generate primary amines. And so it's fairly versatile. Again, I'm sure you can go through the mechanism of this. With the time that we're looking at, I'll just sort of put it up there and tell you guys that this is perhaps a reaction that you guys probably go through the mechanism on. It's not really all that different than what we've seen in the past. if you want to put, say, a mile of proton source to help go through the mechanism, that's fine. So anyways, this is Gabriel synthesis. Again, I think it illustrates two of the valuable things about IMIDs, and if we're going to bother spending the time describing IMIDs, I think this is a really good example of where IMIDs have historically found utility. Make sense? Yes? What about it? Say it again? Rather than the alpha proton? So well, who wants to try to answer that question? So the question is, why this rather than that? 2 reasons. What's that? Well, that's a circular argument. Yeah, it's the most acidic, right, hydrogen, so that's circular, but there's 2 chemical reasons, yeah. So it's resonance stabilized, doubly resonance stabilized, whereas the other ones are only stabilized for the run resonance form. This can be stabilized into this oxygen and this oxygen, where if you deprotonated here, you would only have the one. There's a second, Margo. Yeah, nitrogen, exactly. And nitrogen is just generally more electronegative, right? And so the pKa difference, say, for example, an amide versus, say, butyllithium versus LDA, right? Butyllithium pK is like 50, LDA pK is like 30 or so. Yes? Just right base, yeah. I don't. Maybe next week I'll come in and tell you guys what it is. I forgot to write it down. I think it's just like an alkoxide or something like that. Not something super crazy strong. It's not like you need like LDA or something very strong. I'm pretty sure it's like sodium hydroxide or something like that. Might even be like sodium hydride now that I'm thinking about it. But I'll tell you guys next week. Okay, so in the last 10 minutes or so, we're almost done. Okay, so for the last thing that we'll discuss for carbonyls, again, here's an example of amines. So we just showed how Gabriel synthesis can be used, we'll just say GS, right, as a 2-step process to generate primary amines. Now what if the primary amine that you want to generate, right, this is going to depend upon how you're building up the synthesis, and so depending upon how you're going about a problem like this, you could perhaps change things earlier. But if what you wanted to do is generate an amine and also institute an additional carbon, right? And so if what you needed to add was not just NH2, but within a synthesis, for example, you had a molecule that had 1 less carbon, you wanted to add both the carbon and the nitrogen, we have some options here, okay? And one of them, sort of, at least from a one of them involves a 2-step process that's analogous to what we saw back to the first thing we discussed today, right? Right, if we go ahead and we treat that with cyanide, that's going to give us our nitrogen or our carbon, right? So this carbon is this carbon, right? But what we need to do, right, is effectively reduce the cyano to generate the amine. And now, based upon everything that we've talked about, where everything has been drawn in parallel to previous chemistry that we've seen, we discussed how cyanos can be hydrolyzed in the same way that esters can, what would be a reagent that you might think would allow us to take this compound and generate the primary amine? Somebody that hasn't, yeah. Yeah, and you can do that. Yeah, I'm sure there's a metal catalyst out there that would do that. But more related to, say, an ester. How do you reduce an ester down to a primary alcohol? Lithium aluminum hydride, right? So you're drawing an analogy to an alkyne. It's perhaps better to think about amides. Again, the hydrolysis of the amide that we saw, it might be better to, well, you can hydrolyze alkynes as well under the same conditions. So, but yeah, there's metals out there that would do that. But at least in terms of the textbook tells you, you can do ALH4. And again, you can go through the mechanism at least with an H- source, and you can see reduction, hydride addition into that. You're going to generate the imine, and then that imine is then going to get reduced further to the amine. The other option that you can do that's, again, this would be more stepwise. So I recognize that this is more stepwise, but I'm just trying to tie them together. So again, depending upon the synthesis that you would do, might be longer, but again, if you want to do this in a different way, it turns out that you can also do LAH. And this is where the sort of 50-50 comes out. Like, what happens sort of when you reduce, an amide. And so as it turns out, if you take an amide and you treat it with LAH, you'll actually reduce and you'll generate a primary amine as well. And so with this, following aqueous workup and everything else like that. So in this way, you can imagine a few mechanisms here. Okay, so in this case, right, this would get a little bit more steppy, right? But how would we convert, to sort of finish up today, how would we convert this bromide to the amide? Yeah. So what are we going to do? Sorry. Yeah. Right, so in this case what you would do is you would do an amidation, right? So you basically take this, I think that we will help. Right, so, and we'll see other ways you can make amide couplings from carboxylic acids as well, but this would be the sort of general idea. So why would you want to go about it this way? I don't know. It's just kind of how I tied them all together. But again, the point is that if you take LEH and you reduce it with the amide, you are going to get the primary amine, okay? And so with that, I mean, that will, I think this, even though it's a little early, I think that's a good place to stop. So again, next week, we have quizzes. Next week, we're a little bit ahead. Again, I sort of said earlier, the first day of class, there's not nearly as much material, I think, in Organic 2 in terms of chemistry as Organic 1. And furthermore, hopefully, if you've been tying these all together, it shouldn't really feel like too much new chemistry. Next week, we'll get into enolates and chemistry with enolates if you want to get ahead. So, okay? All right.
Guys, just don't want